Alrighty guys, I'm here to review how we set up a titration in the lab and then also talk about some errors in titration that end up being common questions on the AP exam. So the first thing that I'd like to show you is my burette. Okay, and my burette is here. All right. Okay. All right. Oh, this is crooked. I don't understand how it's crooked or how to fix it, so I'm sorry for that. But this is my burette. All right. I have an open end. This is the stopcock. It controls the volume, whether it's open and it allows liquid to come through, or closed, or any degree of which between, which allows me to control how much I'm adding, and that is very important. And then, although it might be difficult to see, I'll try. You can see that this is calibrated. Each of the major marks are milliliters, and then in between it is by 1/10 of a milliliter. So I believe that that's about, it's quite a precise instrument where you can make measurements with about 4 significant digits. All right. So generally the first step in prepping for any titration is to make sure that your burette is clean and then dry. And the way that we would clean it, now I'm not going to do this right now, is simply by using deionized water. I'd add deionized water here. I'd twist it. All right. I'd sit this straight up. I'd bring it back here to my clamp. I'd open the burette and I'd let the water drain out. Then, once the water's drained out, this would be upside down until it's dry. Now that I can assure that it is clean and dry, I'm ready to set the burette up with my titrant. So that's either going to be my acid or my base. So again, what I would do here, very important, okay, is to add some of the acid that I'm going to be using to the open end of my tube. I would twist it around to make sure that it coats all the glass. Okay. I would put this back into my stand, and then I would open the stopcock and let it all come out. At that point, my burette has been prepped. Okay. Before I move on, I want to talk about the setup here. Okay. One of the setup part that I'm focusing now on is the setup for the burette. Okay. So as I said, it's essential that after I clean it with water, I let it dry. One common error question would be that the student rinsed the burette with water, it didn't dry, and then they added their titrant to the burette and continued to prep from there for their titration. The error in this prep would be that the added water, however much water there was in here, probably not a lot, but it doesn't really matter, will affect the concentration of the standard solution that I have here in my burette. Remember that I'm using information about my standard solution so that at the equivalence point I can determine moles of what I've added. Moles of what I've added will come from the concentration of the standard times whatever volume I'm reading off of the burette here. If the concentration is wrong, then my moles at the equivalence point is wrong. And at that point, whatever I'm trying to calculate as a concentration for my unknown would be incorrect. I want you to think for a moment about how that would be incorrect. Would my concentration, or not my concentration, but my calculated values for moles from this burette be too high or too low? The amount of water that is in here contaminates my standard solution by diluting it. it makes it seem or makes it less concentrated than it should be. That means that I would have to add slightly more of this to my unknown in order to reach the same equivalence point of the undiluted standard solution. That would make it seem like I needed more moles to reach the equivalence point than actually needed. Okay? My calculated value for moles at the equivalence point would be too high. All right. Next, what we have to do is actually set up this burette to run a titration. The way that we would set up this burette is to initially, you can take this out, you would close the stopcock, and you would angle it on its side. And then from there, you would take a volume of your standard solution and you would slowly add it. You could twist this around if you wanted to, but you would continue to add it until you came with a volume that puts you above the 0 mark. So you can see that there's clearly a 0 mark, and you want to have something above that. The reason being is that you have to drain some of it out. You have to drain some of it out so that this bottom part of the burette, the tip, is also full with the liquid that you're titrating with. Okay? You would drain it out until the meniscus is at the 0 mark, and then that way this tip is full and there are no bubbles. If I did not drain it, let's say that I filled it up ahead of time so that it was exactly at the 0 mark without ever draining this, and then I went to titrate, I would have assumed that my initial volume was at 0, but really it was not at 0 because this tip was not full. After I filled the tip, the initial volume on the burette would be something other than 0. All right, again, if I did not do this and I made an experimental error in doing so, it would seem like I added more liquid than I actually did, a greater volume than I actually did to reach the equivalence point. My moles calculation for that reason would be too high. Another example of an error could be in choosing an indicator. So remember, we have to choose an indicator that has a pH plus or minus, a pH, or I should say, yes. We wanted to change color at a pH that is, depending on what we're doing, either plus or minus 1 away from its Ka value. Excuse me. If I were to choose the wrong indicator, then I would observe a color change that is at some point other than the equivalence point. Depending if it's before or after the equivalence point, my error could be figured it out. Or you could, I should say, be able to figure that out. During the titration, you can make errors in reading the burette. And in fact, oftentimes you're given a figure of a burette on the AP exam, and you're asked to make an initial and then a final volume. So it's important to know that initially the volume on a burette will always be 0 or something that you have noted depending on where you are on your titration. And then as you go down, you need to make sure that you understand how to read. Okay, so if it's something between 24 and 25, 24.1, 24.2, 24.3, 24.4, 24.5, so on and so forth. So you're reading from top to bottom, counting from 0.1 up to 25, and not vice versa. Another error could be, even if you selected the correct indicator, identifying where the equivalence point is. So when you're titrating, you're adding small volumes and you're recording information as you go. One of the most important pieces of information that you would be recording would be the endpoint. Now at the endpoint, by definition, that's when the indicator changes color. That's a process that we have to visualize with our eyes. So oftentimes our response time is not immediate. So although we see the color change and we stop, we call that the equivalence point. Oftentimes by the point our brain registers for us to stop, we have actually surpassed the equivalence point. And so we've added slightly more titrant than we needed to. And again, slightly more means that we will have determined or calculated a value for moles, acid equals moles base, that is slightly higher than what it should be. Okay? Well, I hope that this will help you guys in your error discussion or your error analysis and your post-lab questions, as well as we move through these practice titration questions in free response questions. Now we'll move on to the actual titrations. Good morning, everyone. I'm going to be carrying out our first titration, which is that of a strong acid titrated with a strong base. In this case, they're equal molar, 0.1 molar HCl as our strong acid and 0.1 molar sodium hydroxide as our strong base. Recall that both strong acids and strong bases completely dissociate or ionize. So essentially, I am titrating hydronium ions with hydroxide ions, and the product should be neutral water. You can see the graph of the titration curve. There is a steep change in this titration at the equivalence point. So to begin, I've already set up my burette. I have calibrated my pH meter. It's been sitting here in water now. So I'm going to take the water away. I'll dab the pH meter just to try to get some of that water out so that it doesn't really contaminate my titrant. Let's see here. Okay. Here I have a beaker, and to that beaker I'm going to be adding 25 milliliters of 0.1 molar hydrochloric acid. Try to get what I can get out of here. So it's not going to be exactly 25 milliliters, but close enough. All right, go ahead. I'll add my pH meter here. And see if I can get my stir bar to stirring, which it may or may not do. It's not plugged in. Okay. I think this is going to have to be, yeah, I'm going to have to use a smaller stir bar. That's fine. So I've set it to stir. I'm going to wait for the pH to stabilize. I think you might be able to see it. In the meantime, I'm going to record my initial burette reading as 0. I've not added anything yet. And it looks like I can record my initial pH here as 1.38. Since the pH at the equivalence point, or pKa, is 7, I chose phenolphthalein as my indicator. And I am going to add a drop or 2. I guess it says 3, but 1, 2, 3 to my solution. And my color, my initial pH is now 1.34. I'm going to change that, and my color is clear. Now what I'm going to be doing is adding 1 milliliter increments of sodium hydroxide to my beaker, and as I go, I'm going to be recording volume and pH. I'm going to lower this. In fact, I have to get a little bit higher. Okay, here we go. Okay. I've added 1 milliliter. And my pH is actually going down, which means it wasn't ready to start with to begin. 1.29. Don't worry, it'll work itself out. Two milliliters, 1.30. Still colorless. Three milliliters, 1.31. Four milliliters, 1.32. 5 milliliters, 1.33. 6, 1.34, 7, 1.36. Note there's still no color change. 8, 1.38, 9, 1.39, 10, 1.40, 11, 1.41, still no color change. 12, 1.43, 13, 1.46, 14, 1.48, still clear. No, 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 don't get messed up. No. Okay, 15, 1.52, still clear. 16, 1.55, 17, 1.59, 18, 1.64. Slowly but steadily. 19, still clear. 1.70. So note that I'm kind of slowly, sort of getting to 25 milliliters. So equal volume of equal strength, strong acid and strong base should completely neutralize each other, which means as I'm approaching my initial volume of acid with my base, so I'm at 20 milliliters or 19 milliliters, as I get to 25, I should be careful because I will start to see that rapid change. All right? When the pH begins to increase sharply by more than 0.3 units, we need to decrease the portion of the titrant to smaller volumes. All right, we're getting to that point, not quite yet though. So here we're at 20. This is 1.78. So now I'm going to start to slow it down because we really want to capture that steep change. So they want me to go a little bit at a time. I'm actually going to have to adjust this so that I can better see the volume on here. No. All right, so what I will do, let's maybe lower this a little bit. Okay. So I need to add it in 0.2 increments now. Okay, so it's at 20. I need a white background here. A little bit at a time. .2. At 20.2, it's up to 1.80. .4, still 1.80, maybe 1.81. 6. Having a hard time seeing here. .8, 1.82, 21. Okay, I'm at 21. 1.84. Okay, continuing on. Okay, 21.2. 1.85. 21.4, 1.86, 21.6, hold on guys, I'm having a really hard time reading this. I think I made a mistake. Let me see what I have here. Should not have done this by the window. So I started my 1 milliliter increments at 19 instead of at 20. So I will share my data table with you at the end so that you guys have all the numbers. What I'm going to do is quickly continue to move through this. So really this is 20.8, not 21.8. So I'm going to alter this in my data table. 20.8 is 1.90. And now, okay. Okay. 21, 1.90. Seriously, the worst idea ever. Do this here. 21.2. 1.94. 21.4. 1.99. 21.6. 2.02. 21.9. 0.8, 2.10, and 22. 2.14. 0.2, 2.19, 0.4, 2.27, still clear by the way, color. 0.6, 2.33, 0.8, 2.42, and then we'll get to 23. 2.49. All right, so I'm going to have to start using more of my data table. All right, so now we're on to 23.2. 2.59, 0.4, 2.76, 0.6, 2.98, 0.8, 3.44. We're approaching this fast change. And 24. 4.35. All right, here we go. Try and change it from back here now. Point 2. Still changing. pH is 5. Point 4. 5.25. 0.6.
Meredith,
Yeah,
we have a faculty meeting today.
I'm not sure.
Not sure.
5.56. 8. You can start to see the colors changing as I add the base here. 5.77. 25. Almost there. Okay, pH 5.98. Okay. 0.2. So close. .14. 0.4. 6.3. 0.6.
Hey everyone, time to switch classes, and remember for your next class to show your work. The thesis goes at the end of the intro, and then a tomato is a fruit.
6.51. Alrighty guys, I had to pause the video for a moment, and unfortunately I didn't fully close the stopcock, and it's been dripping slowly ever since I stopped the video. Thankfully it's been a slow drip. So where we're at right now is 26.5 milliliters, and the pH is 8.5, 25.6 milliliters, and it is 8.69. So I'm going to keep going here. Okay. And you can see now we have a clear color change. So at 26 point, looks like it's 26.8 milliliters. We're at 9.09. Apologize because this keeps hitting. All right. 9.08. Continuing. 27 milliliters. 9.29. 27.2. Clearly pink now. 9.49. 0.4. 9.57. 0.6. 9.67. 0.8. 9.76. 28. 9.80. 0.2. 9.87. 0.4. 9.93. I think we just keep on moving until we get to about 10. Oh, 12. Okay. 0.6. 2. 10.05. Point 8. 10.08. And after I get to 29, I'm going to go by 1 milliliter increments again. So at 29, I'm at 10.12, and now I go by 1 milliliters. $30, 10.32, 31, 10.49, 32, 10.64, 33. Actually, I overshot that, so we'll call this 33.2, 10.78, actually, I take that back. I didn't get to 33. Now I'm at 33. So 33 is, oh, still 10.78. 34. 10.91. 35. 11.03. 36. Oh. Let's make that 36.5. 36.5, 11.24, and now I'll go all the way to 38. It's because this is taking a while. So at 38, 11.4. I'm going to go by 2 mils now to 40. 11.58, and I'm going to stop here. So that concludes our strong acid, strong base titration. Alrighty guys, I'm here to do the titration of our weak base, ammonia, with the strong acid, hydrochloric acid. Based on the concentrations and the initial volume, which is 25 milliliters of the ammonia, I was able to calculate an initial pH, midpoint pH, an equivalent point pH, and even out here another pH after the equivalent point has been reached. And I have this rough sketch here. Let's see how we do. Similar to the titrations in the past, I'll start with 1 milliliter increments, and then as we approach what I think is the equivalence point, I'll slow down and do smaller volume increments until we pass it. The indicator that I'm using here is methyl red. It's probably hard for you to see, but methyl red is pale yellow in a basic pH, and then it will change color to orange and red at the equivalence point. So my initial pH here is 11.31. I figured it to be about 11.12. So again, perhaps this is a little bit more concentrated because of evaporation over time. This solution was prepared last year. Here we go. 1 ml. Okay. At 1 ml. 10.88. 2 mils. 10.60, 3 mils. .39, 4 mils. 10.22, 5 mils. 10.10. Oops, overshot that. So let's call that 6.2 mils. 9.96. 7 mils. 9.88. 8 mils. 9.78. 9 mils. 9.70. 10 mils. 9.57. 11 mils. 9.48. Approaching pH equals pKa. 12 mils. 9.36. So at 12.5, the pH is supposed to be 9.26, but I don't think that's going to happen. At 12.5, it'll happen at 13. So at 13, it's 9.26. 14. 9.11. 15. 8.96. 16. 8.75. 17. 8.44. So these are starting to change by a lot. I feel like I just might have missed the equivalence point. We'll find out. We're going to keep going. I'll do 17.5. 8.23. 18. Yeah, 7.8. Nope. 7.70. 18.5. It's starting to become acidic. You can see I've had the color change happen here. has really dropped a lot. I'm waiting for it to stabilize. .59. Sure. 19.
Can I go to the office?
Sure. 3.10. 19.5. 2.66. 20. 2.48. 20.5. 2.36. 21. 2.30. 22. 2.17. Go by fours, twos now. 24. 2.03. 26. 1.90. 28, 1.83. I'm going to end it there and take a look at my data. Alrighty guys, we are going to now be carrying out the titration between a weak base, that's 0.1 molar ammonia, with a strong acid, 0.1 molar HCl. You can see here I have our reaction drawn, and I have a rough sketch of our titration curve based on what I know about the substances and their concentrations. So these are a bunch of assumptions because the solutions that I've made are old, and so their concentrations may have changed. That means I may or may not be reaching the equivalence point at 25 milliliters. My hydrochloric acid solution seems to be pretty predictable. I'm worried about my ammonia solution. That means if the ammonia solution evaporated or something, its concentration could have changed. In that case, we may end up meeting the equivalence point sooner or later. But let's get started. And really, in the end, what I'm going to be doing is just paying careful attention to how pH is changing. And once it starts changing by larger degree, then I'm going to start adding smaller and smaller increments of my acid. So to start, I'm going to add 1 ml. So 1 ml. 10.87. I also want to mention that the indicator that I chose for this experiment is methyl red. It's a pale yellow right now. That's its color in a basic pH. And it turns like an orangey red in acidic pH after the equivalence point, or once the equivalence point has been met. Okay. 2 mils, 10.59, 3 mils, 10.40, 1 4 mils. .23, 5 mils, 10.11, 6 mils, 9.99, 7 mils, 9.88, 8 mils, 9.79, 9 mils, 9.68, 10 mils, 9.58, 11 mils, 9.49. We're approaching pH equals pKa. It should occur if they were equal concentration at 12.5 mils, and I have calculated that pH would be about 9.26. So right now we're at 12 mils, and this is 9.38. We'll go to 13 mils. And at 13 mils, look at that, 9.26, which is pH equals pKa. Should be halfway there. At 14 mils, 9.10. 15 mils, 8.94. 16 mils. All right, so now it's starting to change by more. So it's went down from 9.94 to 8.72. So I'm going to start going maybe by half mil increments. .5 mils, 8.61, 17 mils, 8.45. So now I'm going to go by 0.2. .2 mils, 8.38. 17.4 mils, 8.29. 0.6 mils, 8.15. 17.8 mils, 7.96. 18 mils, 7.68. We're getting there. Starting to change more and more. 18.2, 7.39. 18.3, 2.4, and you can see now I've entered into an acidic pH because the color has changed to red. It's still changing, so I'm going to give it a minute. Still changing. Okay, starting to slow down. 4.78. 0.6. 3.29. 0.8. 2.96. 19. 2.76. I'm going to go back up to 0.5 increments now. 19.5. 2.50. 20. 2.34. 20. Oh. I'm going to go up to 21. 21. 2.16. 22. 2.05. 23. 1.97. It's really not changing much. I'm going to go up to 24 and then 25, we'll call it. 24. 1.90 and then 25. 1.86. Looks like we hit our equivalence point very early, so we can think about what that might mean in terms of how these concentrations were off. I'll be back with our polyprotic acid titration. Hey guys, I'm back and I'm going to do the titration of a weak acid. This is 0.1 molar acetic acid with a strong base, 0.1 molar NaOH, sodium hydroxide. I've already set up my burette. I've already set up my 25 milliliters of acid with my indicator, phenolphthalein. Here, what you can see is a rough sketch of what our titration curve should look like once we plot all of our data. You'll see that initially there'll be a relatively steep change in pH, but then it's going to level out as buffering begins to happen. So as we have the production of the conjugate base, the acetate ion, it will back react and kind of stabilize this pH for a while. We'll hit pH equals pKa, and then we'll approach the equivalence point. Okay, so here I go, following really the same procedure as I did last time, adding small increments of base and recording pH. I have the initial pH here. My burette reading is 0, and it is 2.81. I actually calculated what that theoretically should be based on the concentration of acid, and I got 2.87, so this isn't too bad. There we go. Right, 1 ml. Okay. Add 1 ml. And my pH is 3 point. It's still changing. I'm gonna go with 3.28. All right, so note that with my indicator, because this is acidic solution still, the color is clear. Another ml. Okay. So now I'm at 2 mils. 3.59. 3 mils. 3.81. 4 mils. 3.95. 5 mils. 4.08. 6 mils. 4.19. 7 mils. 4.28. 8 mils. 4.36. 9 mils. 4.45. 10 mils. 4.52. We're approaching the pH equals pKa point. So this is 11 mils. 4.60. 12 mils. Now, theoretically at 12.5 mils, it would be pH equals pKa. So at 12 mils, we're at 4.67. pKa is 4.74. So at 13, we should surpass 4.74. Let's see. Yep, we're just about at 4.74. How about that? $14. 4.81. 15. 4.88. 16. 4.95. 17. 5.03. 18. 5.11. Actually, I overshot 18. That's technically 18.2, I guess. I'll write that down. 19, 5.18, 20, 5.28. So what I think I'm gonna go and do is, now that the pH change is getting smaller and smaller and smaller, I'm gonna go another 2 milliliters, and then I'll go and I'll do about 6 milliliters, which should get us through the equivalence point, so that we have some more data points for that very steep change in the curve. So I'm gonna go to 22, 21, 5.35, oh, never mind, 5.40, and 22. All right, so for 22, 5.52. All right, so now I guess I'll start to go by twos. All right. Maybe I'll start to go by halves. Let's go by halves. So this is 22.5, 5.57, 23, 5.63, 23.5, 5.71, 24, 5.77, 24.2, 5.87, 24.4. Oh, I must have read that wrong. It must have been 5.81, because now it's 5.85. 24.6. 5.88. 0.8. 5.90. 25. 5.95. 25.2. 5.99. 0.4. 6.01. 0.6. 6.05. 0.8. 6.09. 26. 6.13. 26.5. 6.23. 27. 6.33. 27.5. 6.43. 28. 6.52. 6.53. 29, 6.8, nope, 6.75, 30, it's lingering, 7 point, never mind, 6.97, 31, almost there. Waiting for it to stabilize. 7.29, 32, 7.86, 33. Let's see if the pink color stays. We're above 8 now because the pink color is lingering. 8.85. 34. 9.24. 35. 9.48. Go up to 36 and then we'll start going by twos. 36. 9.69. 38. 9.94. 40. 10.12. I think we're good. All right, guys, I'll be back with our next titration. Hi guys, I'm back. I wanted to talk to you briefly about the results for the last titration. So if you can see here, all right, here we have the board that I had presented to you earlier. But what you can see here in green is that I drew in the titration curve for the data that was obtained from the last titration. And what you can see here is that the equivalence point was not actually where we thought it was originally going to be. So these are equal molar acids and bases. That means that the equivalence point should occur at a volume of titrant added to, that is equal to what was originally present in the flask, right? So that should have been at 25 mils here, which is why I drew this here in the middle. All right, but what it actually occurred at was a volume that was greater than 25 mils, maybe a volume that was like between 30 and 35 mils. You'll see it when you guys plot your data. The reason why this happened is because here's my acid. I made it last year. And I don't know if you can see this, but there's some condensation and other stuff that's going on in here. And what that is a sign of is evaporation. So as you can see here, I don't even have a very tight seal on here. I should have known better. But most likely what happened was that some of the water in this acid solution that I made last year evaporated, which means that my acid concentration is now something greater, that's 0.1 molar. And honestly, from my titration data, I could probably figure out what that new concentration is. But just to let you know, that is why our data doesn't necessarily look as it was expected in terms of where the equivalence point occurs at. Hey guys, we're going to be doing the titration of a polyprotic acid with a strong base right now. Our polyprotic acid is 0.03 molar phosphoric acid, H3PO4. You can see here that this curve has 3 inflection points. 1 is more noticeable than 2, 2 is more noticeable than 3. We'll see if with our data we can see all of these points. You can also see that I've written out a reaction for the dissociation of each of the phosphoric acid species. First dissociation, second, and then third. All right, let's see how this goes. Initial pH is about 1.98, 1 milliliter at a time. Adding that 1 mil, 2.0, two mils, 2.05, 3 mils, 2.1, yeah, I'm going to call it 2.1, 4 mils, 2.18, 5 mils, 2.30. I might go by half a mil for a little bit. It looks like it's starting to increase. I don't know. Maybe not. I mean, we'll do 1 more mil. 6 mils. Yeah, now I'm going to go by half a mil. This is up to 2.5. 6.5 mils. 2.69. All right, now I'm going to start going up by 0.2, which is really going to be interesting, but 6.7 mils, 2.76, 7 mils, 2.93. Seven point two, 3.1, 7.4, 3.43, 7.6, 4.2. Okay, I think we're approaching, or just hit the equivalence point maybe. 7.8, 4.90, 92, 4.92, 8 mils. 5.20, 8.2, 5.36, 8.4, 5.50, 8.6, 5.70, 8.8, 5.80, and then let's see what we get at 9. 5.90. So now I'm going to start going up by a half a mil instead of 0.2. So for 9.5, 6.08, 10, 6.24, 10.5, 6.37, 11, 6.48. Now I'm going to go up by 1 milliliter. 12, 6.65, 13, 6.83, 14, 7, 15, 7.14, 16, 7.3, 17. 17.49, or I'm sorry, it's 7.49, 18, 7.7. I'm getting close to having to slow down again. 19. Or at 8. So now I'm going to go to 0.2s again. $19.2. Should I take that back? Let's go to 0.5s. So 19.5, 8.17, 20, 8.47. Now I'll go by twos. 20.2, 8.58, 0.4, 8.76, 0.6, 8.89, 0.8. Oh. 9.01, 21, 9.1. I'm going to go up to 0.5s. 21.5. 9.35. 22. 9.55. 22.5. 9.74. 23. 9.85. Gonna go by ones. 24. 10.03. 25. 10.18. 26. 10.3. So now I'm going to go back to 0.5s. 26.5. Actually, I take that back. I'll go to 27. 27. 10.43. 28. 10.52. 29. 10.62. 30. 10.72. 31. 10.8. 32. 10.87. I wonder if this is going to be it. 33. 10.95. 34. 11.02. 35. 11.1. I don't know why I thought the third inflection point was going to be somewhere around 11. I'm going to keep going. 36. I think we're done. 37. It's not changing. 11.2. 3. Maybe I'll go to 40 for fun. 38. 11.29. 39. 11.36. 40. All right, guys. I think I'm going to stop here.